Thank you very much for allowing me to speak to you today on this topic. As introduced, my name is Gary Osmond, and what I'd like to do with this presentation is try to bring to you my 30-plus years in building sciences of understanding construction technology and what matters and how things really work. I understand that part of this problem, I've lost my animation. So there are some slides that kind of made more sense because I could keep up with the flow of the paragraph as we go along, but it's gone, so we'll do with what we can. Excuse me. So a little bit of background. Undoubtedly, we all understand that water intrusion, uncontrolled air leakage, and vapor diffusion, it's a problem. It leads to deterioration, buildings failing, and then all the costs associated with putting things back together again. Our earlier legacy, and I'll blame my father and my grandfather and my grandfather's fathers, of building buildings that are based on, at the time, their best knowledge, their best understanding of construction. And so the issue here is now our legacy of how we are building buildings, and to understand that what the people before us did, albeit the best they could do based on what they knew, doesn't work today. And the primary incentive behind this is the fact that we pay so much money for energy. So we change the way we address buildings, and with that we have to change the way we address how we move forward. So this legacy of I did it before, or I can get away with it, or this is good enough, it just doesn't work anymore. We've got to improve. So construction is really about managing risk and managing expectations and anticipation of the problems that we could face a little bit further on down the line. And I'm sure you've heard this type of comment before, but we need to look at spending on capital cost versus operating cost. If that money doesn't go in at the beginning of the project, then whoever gets to operate the building for, well, what is the life cycle? What is this building planned to do for the next 70 years? We have buildings around that are 300 years old. Can we do it again? Right? But it's how we put our money into these projects and where the money is best spent. We do a lot with buildings to mechanically retrofit them, but unless you take a look at the whole building, excuse me, the way it was designed or the way it was expected to work, when we change it and we change the living environment, you change the way that diaphragm works. Good examples of that is LEED initiatives, where a lot of effort is putting into understanding all of the elements of the building. All the participants in the project are brought together and everybody gets a chance for their proper input. And is there a mechanical engineer in the room here? Okay, do we have an experience? Kidding. I understand from talking to my contacts that with LEED-initiated buildings, there's no longer a heating mode. Most buildings are run in a cooling mode all the time because of the fact that we can save energy and we've done things so nice and tight. And it's not that the building is too tight. There's a connection between the air tightness and the way the mechanical systems work so that they work properly. Your Nemesis, there's another blip from this program. Your Nemesis is that there is a disconnect, in my opinion, between the design professionals and the sub-trades who get to work with us. And there's a reluctance on the part of owners. How many building owners do I have? One? Okay, so don't mean to pick on you, but I'm going to pick on you. There's a reluctance to commission the appropriate technical support. We can't do all this without proper effort by proper people. This effort is not an out-of-the-box situation where you pick A or B or C. It's an accumulated effort by everybody, and that capital cost comment, it takes money to put things into order and make sure that the right people do the design, that the right people are able to be on site and have the time to properly manage and see what's going on, and ensure that the contractors do the job. Because at the end of the day, here's the real question, who's the policing authority in this? Who's the overseers of the work? And all due respect, it can't be the purse strings. It's got to be that we build buildings that are going to last for time You're not going to have that happen if the right people aren't put in place. And unfortunately, it costs money, but it's a capital cost versus an operating cost scenario. Our next issue is our diminishing workforce. There should be no secret we are failing here in Ontario with bringing people in and properly training them so that everybody is on the same page. Our other nemesis is, of course, those who don't attend these events. These are very, very important events to stay up to date, in tune with what's going on in our construction industry, the changes, and the way we build buildings to make them last forever. So understanding preventative measures starts with understanding practical concepts and functional construction. Functional construction is something I'll continue to beat on when I do these types of talks, because everybody in the room has to have a clear understanding of what the net objective is in trying to keep the buildings functioning correctly, keeping the water out, understanding what's happening inside the building environmentally, and what's the impact. It's not a science term, it's a pretty good one. It's called, do you have the wherewithal? Do we have the wherewithal that in the design phase, and more importantly in the construction phase, that everybody understands what's going on? We can insulate buildings, but functionally, if it's not properly insulated, you're going to have condensation problems. We can put up water-resistant barriers, but if they're in the wrong plane of the insulation, you have a problem. So everybody at the table has to understand the functional concepts of the way buildings perform. Failures, and this looked really cool when it was animated, by the way. Our failures, or our causes of failures, are unreliable design systems or systems that have been built wrong through poor workmanship, pushing along. For those of you who get to look at the tender process, when prices come in really, really low, it's got to be the warning bells that there's a problem here. You bought a car without a steering wheel if the price is too low. Things cost money, and we have to be able to ensure that what we are asking for and these specifications are properly delivered. Incompatible products or inappropriate use of those applications. Huge problem. Detailing with the expectations that those details will function. So what is the idea, what was the intent, and can we make sure it's being done properly? A misunderstanding of performance properties. We have a lot of terrific materials out there. They all function incredibly, but unless they're installed correctly, they're not going to work. And the performance properties, it's really looking at board insulation, for example, a great insulation, but it has a permeance rating. Is it the one we want? Are we going to be taping joints? Is that really what you want to do? So it's understanding the redundancy of different building materials throughout the assembly, and are they causing a problem or are they helping us along? Also, specified materials that fall short of their performance properties, either through being installed incorrectly, installed too thin, without proper lap seams. You can see how all these things start to come together. My favorite, it must have been a bad batch. It doesn't exist, folks. The materials that we're using today are great materials, but installed wrong, they're going to be a problem. So we need to design, so this is that functional part again, we need to design based on worst conditions. Again, this was incredible when it was animated. Weather is our best one, and I hope you can appreciate, I ordered up, I conjured up a fantastic rainstorm last night. I want you to think about this. And for the consultants in the room, I know their phones are shut off for a good reason, because people are calling up complaining they have leaks. Right? We have to pay attention to what the weather is. Our weather is changing. We have extreme weather conditions. Take last night's storm and let's move this ahead by 9 months. That liquid becomes a solid. It's snow. Now we've got the wind-driven rains. We've got lots of snow. So what is happening to your building envelope, your roofing membranes, the balcony connection details, the penetrations? Who on earth put that big honking screw for the sign, which now penetrates the entire assembly of problems? Another phenomena we have to deal with is what we've done environmentally. There's a lot of airborne chemicals that create problems. We can put different finishes on metal. We have concrete structures, and concrete's a terrific product, but when you've got chloride ion intrusion and you change the pH level, you have delaminations, you have rust, and you have walls that are going to fall apart. I've got flooding and groundwater here for the simple reason, again, our environment is changing, our weather is changing, we're developing a lot of land, we're putting down hard surfaces, so where's the water supposed to go? We've got a lot of overflow. In Toronto, we have combined sewers, so we have infrastructure problems. And when there's a backup, your owner, respectfully, Mr. Owner, they're not going to take a good excuse that the sewer's backed up. These things have to be appropriately designed for. Settlement is a huge issue. We get SOLS reports. They need to be read and understood, and that anticipated load of the building on the bearing pressure of clays and other materials have to be understood, because buildings will move, settlement occurs. The last bullet point here, human and terrorism. This is not a lecture about buildings who want to knock people who want to knock our buildings down. This is about us becoming unfocused or trying to do something so elaborate with our structures to keep them safe, we lose sight of the building sciences. When you have mass walls and large structures, and if they're not part of this whole concept of understanding how air and moisture may pass through them, we're back at the beginning again. Buildings move. Get over it. The way we build, again, thinking of all the people involved, because it is stick framing throughout the whole process through a myriad of weather conditions, buildings are going to change dynamically throughout the seasons. Materials expand and contract, and then we have this thing called the coefficient of thermal expansion and contraction. Seasonally, things move. I have aluminum shown here, and it's important to understand that this dimension here is the movement per inch of length per degree change. And it gets awfully hot here. We see a temperature swing of 100 degrees from where it is in February. Keep in mind, February, who's ever keeping count, we had no days over -20. And now we go into July, and how many days are we going to have at +30? So metal objects in particular are going to expand and contract. Do you have the wherewithal? Did you pay attention? Did somebody get in there and take a look at these type of conditions and making a calculation that, is this going to break into the wall system? Is it going to fracture? Are my sealants good? Whole host of ideas. The building code hasn't been around that long. Building code was introduced in 1975. This is the Ontario Building Code. So for the longest time we had the National Building Code. Not a bad document, and we've adopted it. We've used a lot of stuff, but you have to keep in mind, that's my bullet point number 2 here, rain control strategies from the 1975 Building Code consisted really of understanding sheathing paper and shiplap joints and make sure there's some weep holes. There was a Part 5, it was blank. There was Part 4, and Part 4 directed structural engineers to do things structurally. So from the 1975 Building Code, we had walls that were R8, ceilings were R20. And what we have to keep in mind today, as you go back and retrofit these buildings, it was the best we had at the time, and we built accordingly. It doesn't mean it's acceptable today, because as you change walls, or you add insulation to these walls, or you change the dynamics with putting different types of weather barriers on, you're changing the way that wall or roof diaphragm is going to work. The earlier days, ASHRAE 90, it was structured and positioned in such a way that it anticipated air leakage. So mechanical equipment was sized to take on that air leakage. In some cases, it was known as the fresh air makeup. So we have heat loss, heat gain, we have heat coming through windows, and the mechanical systems were over-designed for compensation purposes. So there wasn't the acute looking at what we're designing and how the mechanical systems work as we are seeing it certainly today. It was great animated. Things flew around, made more sense. 75 and earlier days, we had 2 types of walls, cavity wall and barrier walls. So I'm going to suggest to you that this early technology, we saw leaks and failures for the simple reason we had a poor understanding of detailing. Keep in mind, back in these days, the cost of gas, the cost of oil, the cost of heating wasn't that much. And we could turn up the temperature a little bit, and any water that come in, we could pretty much dry the building out through heat loss. What a great idea. Well, We can't do this anymore. So this issue of detailing and understanding water control strategies becomes our nemesis as we work forward. There's some principles we need to look at, and it's really understanding the walls that are in front of us. I make this comment because one of the clear things we have to understand moving forward as we look at new construction, it's a small percentage of the portfolio of buildings we have. A very small percentage. So there is actually quite a bit. How many consultants do we have? There's a ton of work in terms of retrofitting buildings that were built based on these three principles here. Mass walls that could take water, store it, and eventually dry out. Exclusion walls that were intended to try to drain water away completely and fully without getting in. And then drainage walls, which we see a little bit more often as certainly as a more successful wall. So to walk through this, we capture a few slides now. I'm giving credit to the OAA Rain Penetration Practice Guide. Great document, great reading. Please be careful. We've changed the way we think on some of the topics that get addressed in there. But I've added slides because they do have a lot of value. Here are examples of mass wall systems, and you can appreciate how they would store water for a period of time. And these are being looked at without the intent or the idea that there's negative and positive pressures that may be happening in the building, sucking moisture all the way through. So we have rubber walls, solid walls, or composite walls. Good examples. Barrier or face sealed walls are curtain wall structures, many around today. Steel clad walls, I call them refrigerator panels, stuck on the side of a building. Good concepts, have to be properly sealed. Exterior insulation is another good example of face sealed walls. Drained walls or screened, so the screening would be the outer layers here that take the abuse and basically stop some of the water from pushing its way through. We have lap sidle, panel cladding, and then masonry veneer cavity wall type construction. We have advanced to the point where we have a discipline now called Building Sciences Group, where we can come to market knowing full well that we have a better understanding of water flow, vapor flow, and airflow as it passes through the assembly. So born out of that is pressure equalized rain screen, as well as watertight, water-resistive air barriers and a drainage plane. These are concepts in design that have to be followed. These are not out of the box. You can grab something and expect somebody to understand. At the design level, the combinations and permutations of the different types of materials here are endless. These are design concepts that have to be appreciated and worked in and tied and connected to everything born out of it. Under this building science regime, we certainly know that mechanical air systems today are being designed and implemented in concert with understanding where's the air barrier and where's the plane of insulation. You can't do one without the other. If you do, you're going to see failures. And so from there, we also get a better understanding of the water control strategies and understand the 5 mechanisms of water intrusion. There's been a lot of changes, there's been a lot of failures, there's been a lot of research. And with that research has come a number of code changes. Once again, this was really cool when it was animated. Part 5, great part of the code. This is taken from today's 2012 code, and I'll read to you the application. This part applies to building materials, components, and assemblies exposed to exterior space or the ground, including those separating interior from exterior or separating interior space from the ground. Also includes building materials, components, and assemblies separating environmentally dissimilar interior spaces, and site materials, components, and assemblies, and grading that affect the environmental loads on building materials, components, and assemblies exposed to exterior space. What a mouthful. I bring this up because in my practices, in my business, as I've seen people come through, somebody has said to me, yeah, the code doesn't say that. Yeah, I think it does. I think it's very easy for us to interpolate and come out of here and looking at this sort of a clause and come back to people, and our owners and say, you know what, these are code requirements. This is what we have to do in order for these types of projects to be successful. Part 5 came from addressing about 7 different topics. We're now up to 11. So it's complicated. The way we use buildings is complicated. The way we build buildings is complicated. And we have to start pulling together, because these are the things that will make these buildings last a lot longer. So back to our original topic, preventative and remedial measures for building moisture. What are we doing, and how do we achieve this? So why now? In the past, we seemed to accept the fact that buildings leaked. We seemed to accept the fact that air got in. We seemed to accept the fact that we could throw money out the window on energy. But it's this red box we're saying, we can't take it anymore. We have to make a change. So the industry reaction is that we're all getting together, we're doing these types of seminars, and we're understanding that in order for buildings to survive, there's a lot we have to do at the design and specification stage. This third bullet point was that this was addressed in 1985. This is not new science. This has been around for a while. The instructions out of the National Building Code in 1985 stipulated that the building envelope shall be designed and constructed with continuous air and water resistive barriers. It made sense there, and it still makes sense now, and this, again, is not new technology. It's what we have to pay attention to. Our sources of moisture, and there might be a few more than my 5 bullet points, but I think the 5 I've got up here make a lot of sense. Your largest source of moisture is going to be during the construction phase, when we take a look at the placement of different materials as you build the building, or inclement water that happens on us during that construction phase. So last year, in 2014, I had the pleasure of building myself a new home, building science guy on steroids. It was a great time. None of the contractors had any clue on what on earth I was doing. The building survived. We've done well. My point here in this slide is that we finished the home in late November, and I set the dehumidifier up. Who has a home with a dehumidifier running? Really? Nobody? Well, then you'll love this. So, brand new home, put the dehumidifier on. It's November. It does. My dad's old Kenmore had a 2-gallon capacity tank. I set everything on high because I know about these things. I emptied it once a day. I sucked 2 gallons of moisture out of my house a day. And I did that for the next 3 months. 2 gallons every day. Then it started to slow down. And I do have to admit, I didn't put it to give me 40% or 35% relative humidity. It's an old Kenmore. It's not that accurate. I put it on high. I was trying to suck out all the moisture because I didn't need the associated problems. I know there's moisture in the building. So I slowed down, coming up around April, coming now into May, and we're getting warmer temperatures, of course, like your basements. My basement's a lot colder because I've got an air exchange, and we all know that cold air drops to the floor. I put the dehumidifier back on. I'm back up to emptying it once a day. That's how much moisture you get in new buildings. A very important thing to consider as we move forward, and somebody's saying, I have mold or I have moisture on my windows. It's what you've built into the building during the construction phase. Things have to dry out. Weather conditions, which is all the time. From this point forward, after the building is done, what is the life expectancy of the building, and have we done everything we can do to keep the weather out? This bullet point number 3 is use and control, or the understanding and control of vapor migration through the buildings. We use buildings. As humans, we exhaust moisture all the time. We cook, we clean, we have offices, we bring in massive amounts of people. Even for this room, with all of you folks in here, we have changed the relative humidity in this room from what it was earlier today. Where is that moisture going? There's pressure differences. It's part of this moisture problem that we're dealing with. Enclosure failures, well, that one's easy. That's what this is about. And then I've got mechanical failures. Now, the comment here, mechanical failures, is more looking at, again, how we use the building, how is the mechanical system set up, and has it been changed seasonally, because what we do in the wintertime is not what we're going to do in the summertime. Is the air conditioner running all the time? Do you shut it on, off? So it's understanding how we as humans live. So measures to control water intrusion is about detailing. It's not the field applications. Problems happen in the details. Joints between dissimilar materials, sheathing boards, any change in direction or change in material, wall openings, top of the wall, is there air able to escape through it? Have you tied the roof into the walls? All these types of problems, and certainly at the bottom, it's understanding what's happening at the foundation level and below grade for us. And my comment here is, similar to roofing and waterproofing, when you do details, when you're putting a system on, it's about detailing first, and then you do your field applications next. Why? Well, because we stick a lot of holes in it. And have you used the right materials that will seal or fasten around all these things in order to give us that water tightness and resistance to penetrations? This isn't about air barriers, but I'm going to talk a little bit about that type of stuff. And so the question becomes, after last night's rain, what's behind your facade system? And did it last? Will it be able to hold the water out after this? Was there wind pressure that may have blown it apart? So the effective approach of controlling rain penetration is that functioning idea of detailing all the joints and penetrations. Water-resistant barriers are shingle lap seams, ship lap flashings, because we know about gravity and water is going to go straight down. But we have to understand what we need on these buildings is watertight air and rain barriers, because it's the mechanism that will provide us a continuous plane of air tightness to guard against the 5 mechanisms of water intrusion. Once again, the animation on this stuff was great. But here we go. Those 5 mechanisms: gravity, of course, kinetic energy, wind, surface tension. We see water travel horizontally on the underside of soffits and balconies all the time. Capillary rise, different materials, and my favorite, air pressure drop or suction through the building. Take last night's rain, let's add a 60-mile-an-hour wind behind it, and there's going to be a lot of leaking buildings. So those are the things we have to guard against. And those are the things that simply shiplapping some material, hoping it works, is not going to work, because one of these guys are going to get in. Right? So these are external forces that happen seasonally all the time, year after year after year. And so the solution is really trying to having that wherewithal, or the functional understanding, a functional concept of constructing buildings properly with all the materials. There was a research paper done by Jacques Rousseau back in 1996, Simulation of Wind-Driven Rain and Wetting Patterns of Building. Awesome reading if you're looking for something to do. He made the point there are 3 conditions that must exist for rain penetration to occur. There must be water, okay, I get it. There has to be a force, happens all the time, and there has to be a path of air leakage or water leakage. The first 2 bullet points are constants. Can't do a thing about it. The third one is the variable. Those are the ones we can deal with. So the question and the challenge back to you is, can we deal with these? Because next week, item number 1 and 2 is going to happen again. It's going to rain, it's going to snow, we're going to have winter, and it's going to repeat itself. Shake and repeat. What we know about moisture: moisture flows through evaporation and vapor diffusion. Vapor diffusion is a function of vapor pressure on 2 different sides of a space, the wall, the envelope. We are certainly clear that hot, moist air has a higher pressure load capacity than cold, dry air. We know that moisture moves from high pressure to low pressure, or it's called equalization. Turn off the mechanical system here, and let's see how warm, how fast it gets. Right? It's equalization. It's one of those phenomena that is not going to go away. It's here. We have to deal with it. Warm air has the capacity of holding more vapor in a gas than cold air. We're clear on that. And relative humidity is the measurement of the amount of moisture an air temperature can hold. So the fact is that moisture passes, or when moisture passes through walls and insulation, because we're insulating buildings a lot heavier than we ever did before. Remember at the beginning of the presentation, we talked about mass walls and other types of walls. They got wet, we turn the heat on, it dries the building out. You can't do that now. You can turn the heat up, and the insulation does a good job. It stops heat loss. And whatever does come through, there's still a temperature change, and that's when you're going to see that vapor go from a gas to a liquid to a solid. And then you call a consultant and say, what happened? So what I'm suggesting to you is we have to look at controlling these moisture transport mechanisms. Vapor retarders are different than vapor barriers. One allows moisture, one stops moisture. We can allow moisture because as it passes, we know that vapor diffusion is okay when there's no air leakage behind it. There's no driving forces. So as always, as we design and develop the buildings, be it the roof, the walls, the foundations, or any other part of that envelope, air leakage is our problem. As we know, air leakage will transport much more moisture than simple vapor diffusion. So let's look at some of the remedial measures as we walk through. And again, please keep in mind as we consider this sort of a discussion, the number of new buildings we build is significantly less than our existing portfolio of dilapidating buildings. And we have to start doing things to these older buildings so that they will last longer, they will be energy efficient, and they will serve as they should. My friend Joe Stevebrook, he's come up with this sort of design, and his push on stuff was looking at all the connection details, all the joints, because it's at the joints and connections you have a difference of trades, different people walking in with different responsibilities, and I've done my job, that's good enough, thank you very much, I'm out. That can happen, we have to look at those. So penetration, sheathing board joints, the junction of dissimilar materials, and the junction of dissimilar systems that are intended to keep the water out or keep the heat in. Penetrations by utilities. So back to my home, tried everything to keep everybody in touch. I pre-planned every hole in the foundation so that I could properly seal it, and when we finally were about to get occupancy permit, had to call the city. They put a water service meter in, and before my wife could stop him, he come up with a 14-inch long drill and went straight through the foundations. I had a hole over there ready for him, but that wasn't in the right spot. Utilities come in, they make a penetration. So this is that disconnect I talk about. People have their own responsibilities and ideas, and they're not yours. But we have to plan and pre-plan and have the foresight and wherewithal to ensure that we can look after all these types of details. There's these parts of the building I quickly want to address as we look at retrofit and remediation. Roofing, sealants, walls, waterproofing, and in all of these, it's about long-term durability. What is that? What is the life cycle of the products? What is the life cycle expectation on the part of the owner for us to complete these projects? So there's a number of things I want to talk about, which are going to be our design considerations. From the owner's requirements, what are the service conditions of the materials, what kind of system, what kind of surface are we putting it on top of, and what are the substrates? Are they something that we can deal with? So from the owner's perspective, life expectancy. How long, I'm paying this much money, how long is it going to last? What are the finishes? What are you looking for? Can we accept certain things, or are we pushing for a higher bar? Are there installation constraints, be it traffic, be it it's a usable building? What is the budget? What is the warranty behind it? All these need to be addressed before we can start taking a look at any type of remediation program. The service conditions of the materials we're trying to retrofit would be its use, or how much abuse is going to happen over on this material for its life expectancy. Is there chemical resistance issues, be it airborne or be it a traffic deck, be it oils and gases? What's its exposure? UV stability, always a big issue. Movement of the building, and thermal shock. Going through different climate changes, we can use it now, but how does it hold up in the wintertime? Or conversely, how is it going to hold up in the hot sun? The construction types or materials that are on, the substrate material, deck, sheathing board, concrete, steel, EIFS, What are these materials? How are they going to react? I come back to the use and occupancy of the building. It's us. It's what we do to buildings and how we live in buildings or survive that has an impact on this wall system itself. How are we dealing with penetrations? Is the repair horizontal, vertical, overhead? And what's our access to it? All questions that have to be asked. In terms of existing conditions of the building or what has to be retrofitted, and this was great in an animated mode. I was cool with it, but here we go. Surface strength, efflorescence, does that have to be cleaned? How's it going to be cleaned? Again, dealing with the joints, the cracks, the voids, pinholes. Putting materials down, does it create pinholes, or do you have other problems with it? Connection to similar materials, and does it drain? Systems have to be drained. Horizontal surfaces have to be augmented or changed so that they're not going to collect water. Water's going to be able to drain away or have some sort of disposal system. Once again, the animation worked. My point here was in roofing systems, it's about all the different types of connection details you have to work with. Roofing has to be understood, and it's not a hit on roofing materials. There's a lot of great products out there, but they eventually break down over time. Give it 15 years, give it 20, give it 35 years. But roofing is one of those necessary evils that have to be put in construction budgets as something that would be maintained or replaced at some point in time. You only want to have qualified people up on the roof because of the logistics and the liability of dropping wrenches, dropping equipment, or making a puncture, because the trade who makes the puncture is not his fault, of course, somebody else's. You need to do maintenance, you need to do visual inspections, you need to make sure that that roof, and again, it's not a slam on roofing, it's understanding how building materials perform long term, and eventually they need to be replaced. Sealants is another one that fit within that sort of category. Sealants is a very, very small total cost to the project. Miss them, and it is a very large source of aggravation. So picking the right sealants and ensuring the sealants are applied correctly is a monumental task and certainly needs a lot of attention. I've got weather seals, I've got joint seals, and I've got seals that have just lasted more than what they can take. There was actually two shots here. One was showing fixed joints or weather seals, and then there's this shot that was nicely sliding on top that shows joints that move. It's a very important consideration in looking and picking sealants, because again, there's fixed joints that don't move, so dynamic joints versus static joints. Did you pick the right sealing? Does it have the elongation? Is it the modulus you're looking for? Buildings move. Sealants go under a lot of stress. Consider a building, a plate of armor with segments to it, and the sealants are the materials that are going to hold and keep those segments watertight. So sealants are subject to longitudinal shear, transverse shear, compression, extension, normal flexure, parallel flexure. Things move. Sealants are there to pick up that movement. Have you picked the right one? Does it have the time expectancy that you're going to be looking for? I've got two shots here. The first one is a failure. Any sealant manufacturers here? It fails. It fails because of this thing called the hourglass shape. On this one, which is the correct one, I've got great bond there, I've got great bond there, and I've got a little bit of material here. That's correct, because as things move, where it's the thinnest, that's allowing the movement. With this one, I've got incredible bond, and too fat of material, so its modulus, or its ability to move, is compromised. And when there is movement, you're either going to get an adhesive failure or you're going to get a cohesive failure. This is one of those times that more is too much. Sealants have to be applied properly in order for them to work and last the duration. Understanding the use of sealants in conjunction with other materials becomes critical, because some urethanes and silicone sealants are not compatible with SBS modified membranes. There's plasticizers involved, and one will make the other one start to flow and seep out. In law, I understand this is called black gold. because it's going to be a huge thing to try to fix later on and come back and remedy. Wall repairs, different options, but when it comes to walls and wall construction, your options to do maintenance or your options to do a quick fix doesn't exist because you're limited to the types of options that are in front of you. The most expensive, of course, is going to be strip down the facade and start all over again. Overclad the facade with an EIFS system, or look at different types of elastomeric coatings. You can appreciate each of these have a different cost factor to it. One is going to be significantly larger than the others. We can do full cladding replacement systems. With these, you get a continuous water-resistive air barrier, you've got the drainage plane, insulation, laminas that are non-combustible so we can meet code regulations, and with these you can give the building a new look at a relatively effective cost. With elastomeric coatings, and there's a number on the market, the avenue here is to ensure that you are able to make a continuous connection up and over and around the frames to tie into other materials. Elastomeric coatings prevent water intrusion when applied. And there's coatings versus paints. Paints go on thick, thin. Coatings go on thicker. They need some body because, again, buildings move and you need those elastomeric properties. These coatings need to be vapor permeable or breathable. Chances are there's a plane of insulation in there somewhere. They need to be carbonation and chloride resistant and have crack bridging properties, and most of them have fantastic weathering properties. Acrylics, again, as a coating, going a little bit thicker, used as protective paints, balcony coatings, floor coatings, wall coatings. Acrylics are in the adhesives and sealant business as well. They are highly resistant to weather damage. Excuse me. Don't turn yellow or crumble. Have good impact strength, solvent-based, water-based. So good options in front of you. They become breathable, very tough, durable materials, go on at any temperature, or at low temperatures rather, and come in a variety of colors. So again, an option that's relatively low cost, but give you some good options on good return. Silicone coatings is another material that is out there, thermally stable, go on at low temperatures. These are UV stable as well as very breathable type materials. Silicone coatings make things water resistive. They don't make them water tight. Okay? Silicone ceilings, silicone materials are good to shed water, but you do not want to be using these on horizontal surfaces because long term, and that's what this is about, long term, you could see issues down the road. Waterproofing options have certainly changed, and you have a variety in terms of acrylics or polyurethanes for waterproofing membrane systems. They are UV stable. Without it, we have problems. Water gets in, things happen, concrete breaks off, all sorts of cracks. There's cracks in these T-bars, and then there's real cracks. Things fall apart. Water gets in, breaks it down, you have a problem. Urethanes come in different degrees or types. They're typically two-component materials, and the point of this slide, they come at different costs. It's understanding some of these terms that are used when you're taking a look at the data sheet. Which one do I want to use? Aromatic isonates, this is a product that increases or slows down the curing process, but aromatic isonates, they will interact with visible light and discolor, turn yellow. That's not what you're looking for. When you take something that has aliphatic isonates in it, these make materials more UV stable long term. There's a number of applications where we see these types. Again, they're two-component, odor-free, 100% solids. Use them in a variety of applications, but then you would broadcast some aggregate on it. If we take a look at the traditional mod bit or hot rubber type applications, great waterproofing membranes, but they have to be protected from the light, and other materials have to be added on to them to make them walkable. So now with the urethanes, you can switch that around a little bit, and they certainly get used for a number of different types of applications. So in review, deficiencies in the enclosure are going to create problems for us. As moisture is going to get in, you're going to increase your operating costs because maintenance is an issue, and you're going to see deterioration of building components over the short term or over the long term. So these preventative measures that I'm talking about are a systems approach. It's not a product that goes on. It's taking a look or having the wherewithal as you're looking at the product and the project and the deficiencies to ensure that everything works together. The water-resistant barriers or any type of system that goes on the buildings to keep the water out must be flexible and remain flexible long-term. So to avoid problems, go back to basics. Understand what are the materials, what's the substrate, what's the expectancy, can it be implied, what's the building use, what is the building use, what are we using this for, how is it going to affect the performance of these materials, are we creating a plane of water tightness or not, and look at all the connection details from roof to walls to foundations. Please read manufacturers' data sheets, understand what we're saying, understand how these materials are to be used properly. I personally think that specifications is the correct way to ensure this work is done. Spell it out, list it, draw it properly instruct the other person who's going to be doing this what your expectations are and how these systems are supposed to work. And then talk to manufacturers you can trust. Thank you very much.